So, can everyone see that?
Yep, I can see it.
Okay. So, let's see. And, okay, can you see this? Singular values of convolutional layers.
Yep, looks like everyone can see it.
Okay, great. So this is the paper that we're going to talk about. And I'll start by giving a very, very high level introduction to the paper. So a 3-sentence kind of introduction to this paper. And so the generalization of a convolutional deep neural network can be improved by using a new form of regularization. So generalization is the ability of a network to perform well on unseen data. So it's not enough to just train it on training data and get a good result. We want it to generalize. And so this paper is about regularization. So in this particular regularization that is developed in the paper, limits the intermediate network activations. And if those are not constrained, they can lead to exploding and vanishing gradients and other problems as well. And finally, for a practical point of view, the regularization developed can be computed efficiently and used within the training cycle. So a lot of the paper is pages of the paper, and certainly a lot of the mathematics of the paper are concerned with this efficiency. All right, so that's 3 sentences, very high level, and here's a little bit deeper level, and this is kind of matching what the abstract talks about of the paper. You know, a very high level introduction. Deep neural networks that are used in image processing are compositions of convolutional layers with intermediate non-linear processing layers. So I'm sure that if you've been using different types of platforms like Keras or that you've seen software that's specialized to these kinds of things. So now that I mentioned that these are compositions of convolutional layers. So this paper is really concerned about the convolutional deep neural networks. Fully connected networks are not so much the focus. And it's the convolutions within the network that allow us to control these transformations. So these convolutions, which we'll talk about the details of what it means to convolve, they are really just linear transformations. And so as such, they can be represented by a matrix and can be decomposed into by this technique called singular value decomposition. So the convolutional structure of a network layer is equivalent, as I've just said, to a linear transformation and with a matrix representation. But it's a special matrix. It has internal symmetries to it. It's not a symmetric matrix in the linear algebra sense, but there are internal symmetries that are very important that we can take advantage of. So the advantage of having this symmetry in the matrix is efficient computation of the singular values. And also this representation, this SVD representation, allows us to look at the transformation in factors. And one of the factors, it's very apparent what the range of the transformation is. So this SVD allows us to characterize the range of the transformation. And then if we can characterize it, then we can control the range of the transformation and limit its output in a principled manner. So principled meaning that we understand the transformation, and so we can control it. So using this modification, this modified transformation during training leads to better generalization. So that's one of the very first bullet points that I made in this slide is generalization. And so that's the idea here, generalization. And finally, the paper will talk about experiments that were performed using CFAR10, and that led to an improvement from 6.2% to 5.3%. So I did some computation, and that's 14.5% relative improvement, which is not bad. So this next slide is just a very basic introduction so we can just kind of talk about terms that we'll be using. And so here's a typical CNN, convolutional neural network, an architecture that's used for image classification. This is kind of an old one, but the important things that we're going to be talking about are these green layers, and those are the convolutional layers followed by the ReLU. So this is the nonlinearity that was mentioned earlier, but the convolutional part, as we will see, that's just a linear transformation. So I'll just very briefly talk about this. This is just a, an overview of what convolutional neural networks do. This is, you have two kinds of things that you're interested in doing. You have an input and a convolutional kernel, and you get an output. So this convolution is sometimes denoted as an operator with a star. And in this diagram, we can see that if we apply this yellow convolutional kernel to this image centered at this point here, then we just multiply it component-wise. So 1 times 1 plus 1 times 2 plus 1 times 3 plus 1 times 1 plus 2 times 2 plus, and so on. So there's 9 multiplies, and then they're all added together. We get this 20. So it's a straightforward operation, but there are a lot of them to be done. So it all adds up. And in the convolutional neural networks that we typically use, these kernels are 3 by 3 is used quite a bit. And in the older ones, they use something like 11 by 11, so large. And then the inputs, well, I'll go back to this slide to show what the input is. At the very top level, we have an image input. And those are, typically this is a 224 by 224 by 3. The 3, of course, is the color planes. So it starts out large and shallow. And as the network progresses, it shrinks in this maybe spatial dimension, but grows in this channel dimension, right? So the nomenclature that's used a lot in this paper is N for this spatial dimension, and N for the spatial dimension, and M for the for this channel dimension. Okay, so this example is just the channel. There's only one channel, so we're not going to talk about max pooling or whatever. So this is the important thing here. Another, just a very brief introduction to what deep learning does. It's, you know, we've got some objective function, and it's defined over a parameter space, and we're interested in finding the minimum of this objective function in the parameter space. And so we do that by computing a cost function, and then at a point in the parameter space, and then using a gradient of that with respect to the parameters, moving our point in that direction, or actually in the opposite direction. So this is our learning rule. We have these weights of the network, parameters, and we're adjusting the parameters from the parameters in time t, or step s, step s, to the next step, s+1, using this very simple learning rule that I've described here, where we're proportioning our step by this learning rate alpha. So finally, in this paper, for what we might call singular value learning, the update to our weights is done by using the kernel components. Let's see. So here's some terms that I just wrote down. I won't go through them all. We'll just pick them up as we go. But you know, these are some things like, you know, singular value decomposition, circulant matrix, Fourier transform that maybe aren't. It could be new to you, so you can maybe look those up. And also, I would recommend, like, there's a lot of notes in the paper at the end, but he does mention at the very beginning a book, and that is the book called Deep Learning by Goodfellow. And that book has a lot of this information in it. So if you just need a single place to look things up, I'd recommend going to that book, which is available online for free. So, okay, so a little bit more about the structure of how we want to train and regularize. So we're going to train the network with gradient descent. That's nothing new about the paper. It's going to use some form of modification of the weights of the network, of the parameters of the network, and but we're going to use this special regularization in the training, and we're going to adapt the network layer's linear transformations, which are typically represented as convolutional kernels within the software. So for example, like if you're using TensorFlow, it's running on a GPU, the convolutional kernels are what are implementing these linear transformations efficiently. So we're going to restrict the ranges of that, and that's going to create some regularization. So these linear transformations that are corresponding to the convolutional kernels, they're decomposed with a singular value decomposition. So we'll go into some details on that. And the singular values can be computed efficiently just using the kernels. And so then we need a linear transformation in order to do our forward propagation through the network. So we recompose that transformation after we've done this singular value decomposition and after we've limited the ranges. So I think that this is analogous to spectral domain filtering. So if you've ever thought about that, or, you know, it's very common. It's been used for decades and decades. So we'll talk a little bit about that. But that's one way to look at things, is this, you know, sometimes called frequency domain filtering. And okay. So some reviews on what a convolution is and how it corresponds to linear transformations. And at some point, I'll bring up a Python notebook with some real stuff. So, so a convolution is a linear transformation, and because of that, it can be expressed as a matrix. In one dimension, a convolution has a matrix that is circulant. So that's, oops, sorry. That is circulant. So we'll describe what that is in detail, but that is an internal symmetry in the matrix. If we have a two-dimensional convolution, then the matrix that represents the convolution is called doubly block circulant. And so what that means is that at one level, there are circulant blocks rather than circulant elements. In the one-dimensional case, what's circulant are individual coefficients, individual matrix elements. In the two-dimensional case, there are blocks that are circulant that this internal pattern represents, and then each of those blocks is in turn circulant. And then in 3 dimensions, you know, this extra, what we might call the channel dimension is added. Then we have a matrix with another level of circularity. And so I have a diagram that describes that. And I can bring that up in, let's see, maybe I'll bring that up now, just to, might be a good point to, so I put together this diagram for the 1D case, the 2D case, and the 3D case. And so in the 1D case, we have just sequences. You know, we put in a sequence and we convolve it with another sequence and we get a sequence out. So maybe X is the input and Y is the output, and some convolutional kernel is used. And let's see, you might want to bring up your diagram. This is perhaps small on the screen, but here's the, you know, Y equals X star A. So what does the linear transformation look like? Well, in convolution, it would look like this, where it has this pattern of where each row is shifted by 1. And so that causes diagonals along the matrix to be identical. So we can simply do this convolution by a matrix multiplication. So we take our X, which is a vector, multiply it by this matrix, and we get a vector out. So it's a linear transformation, a vector in, a vector out. And the convolutional kernel, we met in the paper, it's represented by K, like capital K a lot, but also small k is used to denote its dimensions, like it's a K by K matrix. But as I mentioned in the paper, this is embedded into an n by n matrix. So you take all these coefficients and you basically put it into an n by n in a relevant position. And things outside of this K by K matrix are 0. So in the two-dimensional case, instead of a 1 by n signal or an n by 1 signal, we have this n by n signal. So that that results in a convolutional kernel that is not block circulant element-wise, but doubly block circulant. So there are n blocks. So n is like, corresponding to the dimension of this input, n by n. So there are n blocks. And each of those n blocks, say here's a block, that has this simpler structure that the 1D had. So the whole matrix then would have n squared by n squared elements. So now, how can you do a 2D convolution by using this matrix? Well, the way you do it is you take this matrix X and you kind of unravel it. So that's this vec notation, vec of X. So you take this matrix and turn it into a vector simply by taking the columns and stacking them. And so if you stack the columns and multiply it by this matrix, you get a vector out, and that's Y, but it's in vector form. So you would have to unstack it to get your two-dimensional signal output. So in three-dimensional signals, you have, again, n by n, maybe these spatial dimensions, but then you have m channels. So for like our typical application, this is an image, and there are 3 channels, red, green, and blue, the color channels. But it's important to remember that that's only at the first level. As I showed in one of these diagrams before this diagram, as the network progresses, it gets deeper, the channels increase, and the spatial resolution tends to go down in many networks. So, but finally, what does the linear transformation associated with this 3D convolution, what does it look like? Well, it has m by m blocks. So that's the number of channels. And each one of those blocks looks like a two-dimensional doubly block circulant. And then, of course, those have the structure of the one dimension. So this, I've done a little bit of algebra here. And you can see that it really adds up, right? I mean, the number of elements in this matrix is, I believe it's m squared n to the 4th. So what are these typical values for m? Well, m is, it starts out at 3, and n starts out at 224. So that's a real big number. So this is the number of elements in this matrix is large. So if we were trying to do matrix analysis on this, I think it's maybe 50,000 by 50,000 matrix, or well, I don't know, it's big. That would take a long time. So a lot of this paper has to do with doing it not in this matrix transformation space, but sort of in the kernel space, where the kernel is much smaller, right? The kernel is maybe 11 by 11, as opposed to this huge matrix here. So, okay, so that's the diagram. Let me get back to the slides. So let's see. We've talked about, okay, I'm going to talk about singular value decomposition. And the notebook has some stuff as well that I've talked about. We'll go over that quickly. We're about halfway through, so I'll try to speed things up maybe a little bit. But okay, so any matrix can be written as a product of three matrices, each with a specific form. So SVD, you know, that perhaps is related to eigenvalue, eigenvector decomposition, whereas eigenvector decomposition is restricted in its use on the type of matrices that can be decomposed. This SVD can be used on any matrix. So this is what happens. You have a matrix A, and you can decompose it into three matrices, U, D, V. So there's a different, like a specific structure to that decomposition. So here's our M by N matrix, just a general matrix. You know, it's not a square matrix. It can be, but you know, in general, it's M by N. So U is what we call the left singular vectors, and the vectors are orthogonal. D is an M by N diagonal matrix of singular values. So that's the singular values are kind of the name here. And V is an N by N matrix of right singular vectors, and they're orthogonal. So, so it's M by N, M by N, and N by N. So you can see if you do these matrix multiplies, you have M, M, these M's match, and then you go to N, and then these N's match. So this final result is M by N. Okay. So what do these matrices mean? The transformation can be thought of as a rotation by V, followed by a scaling by D, and finally another rotation by U. So these rotations are not changing the vector's length because they are unitary, I believe. But what changes the vector's length is this mid matrix, this scaling matrix, which is diagonal. So the rotations preserve the norm of the input. So they don't change the input size. Only the scaling transformation controls the magnitude of the vector, which I've referred to as range in the past. So this is perhaps the way we can think of it as our principled way to do our regularization, because we know that we can control the transformation by looking at these ranges. So this is a little bit of a way to understand what I mentioned before, like doing things in this frequency domain or the spectral domain. This is not directly what's being done here, but I think it's worth just quickly going over this, you know, to get the basic ideas that are used in the paper. So the convolution of two sequences is related to multiplication in the frequency domain. So if we have X and K, if these are two sequences and their convolution is denoted by this X star K, we can also express this as the inverse Fourier transform of X and K, capital X and K. So capital X is the Fourier transform of the sequence X, and capital K is the Fourier transform of the sequence K, as I've denoted here. And this F minus 1, that's the inverse. So we can do convolution by multiplying, by first transforming into the frequency domain, multiplying component-wise, and then inverse transforming. You might think, well, that's a lot of trouble, right? This is just a summation. Seems easy to do. And then this involves like Fourier transforms, inverse Fourier transforms. But turns out that there's a special kind of transform that can be done called the fast Fourier transform, FFT. And that can be done in n log n time, as opposed to convolution of n squared. So that is like key to the algorithm that's presented in the paper, this FFT. So here's an example of the use that I've mentioned before. It's called filtering in the frequency domain. So we can transform the sequences to the frequency domain, do the multiplications of the sequence by a window that attenuates selected frequencies and then inverse transforming back. So that has been used for like, I don't know, maybe 100 years or a real long time. You know, you can think of like in audio, for example, a one-dimensional signal. You can transform the audio signal into its spectrum, and then you can selectively attenuate spectral components, and then transform it back. So a high-pass filter, it can be used by like a window that attenuates the high frequencies. A low-pass filter is just the opposite. It attenuates the low frequency. So you can get rid of like rumble in something by doing this frequency transformation. And then in two-dimensional signals, common filtering that we might want to do. You might have a blur. So you might have a kernel that's just all ones, right? So that's a filtering. You can think of it as blurring, and then another kind of filter that you might want to do is like an edge detector. Like that would be a kernel that has like differences in it, like pluses and -1 along a certain axes. So you run that filter over an image and it enhances edges. So you can think of that as enhancing frequency. Anyway, so, well, okay. So this is, we'll go over this slide. It's important to the paper, but before we go to that slide, let me bring up the notebook. And it has some stuff in there that I think it's kind of useful to play around with. So here it is. So it uses NumPy, and it uses SciPy, a couple of things out of that, and it does some plotting. So it doesn't use much. Okay, so this is one-dimensional convolution. And we're going to convolve, say, a sequence F and G. So there's a lot of, some of the complexity of this stuff results from the use of many different names for the same kinds of things. Like a sequence, well, that looks like a list, which looks like a vector. But it's just important to think of it as, a mathematical kind of thing. So here's the definition, mathematical definition of convolution in one dimension. Here's the star operator. So this means that FG, the nth element of the convolution of F and G, is equal to this summation. So this is kind of a mathematical definition that is uses infinite, negative infinity, positive infinity, but in general, F and G are a finite support, right? So that means that there's only a finite set of non-zero values within F or G, so that this infinite sum is really, you know, it results in a finite kind of sequence, because everything outside of certain range is zero. And, you know, typically, if we're interested in images, they're bounded as well. So if we want to convolve F and G, we can simply use this num-by thing called convolve. And when we do it, here's the output. So one thing that I want to bring up is that this definition of convolution reverses G. But typically in neural networks, we don't reverse the kernel. And that's, that would just be extra computation, and there's no point in doing that computation. You can just think of the kernel in the reverse manner. So I think in the paper, and as well as a lot of neural network literature, they don't reverse the kernel, but mathematics, they would probably call that a cross correlation rather than convolution. So circular convolutions can be done as well by doing this, but we'll talk a little bit about that later. So what I'd like to talk about in this cell, I didn't write this cell, I found it on the internet, but this is a program that will produce the convolutional matrix from a kernel. So that's basically the circulant matrix we were talking about. If you give it the kernel, it outputs the linear transformation matrix that can be used. So I just want to show how that can be used. So we take our G, we're assuming that, like, say, G is our kernel. So then, excuse me. So this is G, our kernel, -1, 0, 1. And we're going to convolve that. We're going to come up with a matrix that represents that. And here it is. So CM looks like this. First of all, it's 7 by 5, and that's what it looks like. You can see it's circulant, right? It has this circulant structure. And if we use that that matrix CM and we multiply it by F, we get, I've called this convolve FG2, and you print that out. So how does convolve FG1 and convolve FG2 compare? Well, they're pretty close according to this. So that means if we use the regular convolution here, you know, convolve it with NumPy, or we compute this linear transformation matrix, and then we just do a matrix multiply, we get the same thing. So this is the basic one-dimensional example. Okay, so let's do a very fast singular value decomposition. So in this case, we just generate a random n by n matrix. We use this NumPy linear algebra SVD package. It breaks it into U, S, and VH. And here are the dimensions of U. It's 9 by 9. S is a vector, and VH is 6 by 6. So in my slide before, I think everything matches up except for this. And that's because it's sort of, it has because it's a diagonal matrix, it's just, giving you the diagonal components. And here's what they would be, right? So notice that they're ordered. You know, that's the first one is the biggest, then the next. So this is our scaling. So S is representing the scaling of this transformation. And so this is the biggest scalar, is the first one. So they're ordered. Okay, so VH, that's this right-hand side singular vectors. That it looks like that. I just done something that shows that if you take VH and take its transpose and multiply them together, then you get this identity matrix. And it's, you know, these minus zeros, that's a very, very small negative number. So, but for the most part, it's the identity matrix. So just very quickly, we can show that if we multiply these things together, that we get back with what we started. So what I have to do then is I take the S, which is diagonal, and I embed it in an M by N matrix. So now it's the rank that I talked about in the slide before. So now we can do the U and S full rank VH. And we look at the shape, it's 9 by 6 of the output, and we print it out. And now we use this to compare it. So this A SVD, which is recomposed, is equivalent to our A. Okay, so here's another like little one more thing. In the paper, they mentioned that the eigenvectors of they talk about the eigenvectors of a circulant matrix. That's very important to the efficiency of the algorithm, is knowing this fact, that the eigenvectors of a circulant matrix are Fourier basis vectors. Okay. And we're going to show that the eigenvector elements are equally spaced in the complex plane. So, which, you know, means they're Fourier basis vectors. So we're going to start out, the idea is we're going to create a circulant matrix of a certain size. So 32, it's going to be a 32 by 32 matrix. And we're going to use this function that I referenced at the top to do that. So we call this, and it creates this circulant matrix M, CIRM. Then we're going to use this eigenvector package to factorize it. And we're going to look at the shape of those things. So W and V have this certain shape. And then this is just to show you that if you take V and you multiply it with its, you know, complex conjugate transform, then you get the identity matrix. So the other thing that, you know, the whole idea is that we want to show that the circulant matrix eigenvectors are Fourier basis vectors. And so we can visualize that by this plot where we take the real values of the eigenvectors and the imaginary values, and we create an X P list and a Y P list. And I'm just scaling it by the number of the square root of the number of the components, and that because that makes them all these vectors. Well, okay, so of course these are complex numbers, right? Each element of the Fourier basis vectors are complex numbers. So they have this like phasor representation, right? They have like one component is the real and the other component is the imaginary. And so if you plot those complex numbers in the real and imaginary plane, this is what they look like. So you see they're little dots equally spaced. So that's saying that these are kind of like these Fourier basis vectors. And so each column, like the first column might be like that. The next column is maybe shifted. So it's the same thing, you know, just kind of shifted. So it's interesting to note, you started out with a circulant matrix, that it has a certain internal symmetry to it. And then this, its representation in the eigenvector representation or factorization also has like this symmetry to it as well. I won't talk about this. This is actually from the paper. This is their definition from the paper. So it's, you know, it might be a good place if you want to continue on to like play around with this, this thing here. So I'm going to go back to our paper. And so we talked about singular value decomposition. We talked about multiplication, the frequency domain. So now this is going to be directly from the paper. And it's called, you can think of it as this, the regularization they talk about in the paper. We can call it regularization by spectral operations. Okay. So if we have the kernel of the convolution for a specific layer, we can take an FFT of that. And so that results in, say, we'll call it A. And then, of course, A is just any matrix. It can be represented, or it can be decomposed by singular values into U, D, and V. We saw that in the Python notebook and in the slides. Now, D, we talked about D, right? That's the diagonal components of the matrix. We can clip those components, and we'll call that D tilde. So we're kind of clipping the transformation, like limiting the range. And now if we take these things and recompose them, then we get a new matrix. Maybe you could call it A tilde. But then we inverse FFT it, and we get this K tilde. So it's not the same K we started, but it's similar. In fact, as I noted in the text, that if we clip the values like at infinity or something, you know, then we're not changing D at all. And so K is the same, right? So we're just doing a Fourier transform and inverse Fourier transform. So we should get back what we started with. So you can kind of see that as this clipping threshold comes down from infinity, it has more and more of a regularization effect in that it tends to change K. Then finally, we're back in our original domain, K tilde. And so we window that K, right? Because this K can have components, elements outside of its of its K by K original kernel. You know, some of the N by N elements can be non-zero due to the way this transformation works. And so we window it. We basically just set those components to 0. So now we have another kernel with subscript W. So I'll just go through this again. The kernel of the transform is denoted by K. So this linear transforms that's used with a convolutional kernel is this capital K. We do an FFT, we do an SVD decomposition, and we have this diagonal matrix D, which controls the range of the transformation. We clip D, and then we transform it back to the original domain. As I mentioned before, if there's no clipping, then K tilde equals K. And then we window, because values outside of the K by K region should be set to 0. So in summary, a new kernel is created by clipping the spectral representation and then windowing the inverse spectral transform. The new kernel's transform is a bounded operator norm, and it's bounded by these clipping values. So that's kind of the heart of our regularization, which is employed in our training. So finally, the paper talks about experiments. So the first thing is just timing. And they look at the comparison between the full matrix method of factorization with these FFT-based methods implemented in NumPy and TensorFlow. So I believe that if you look at the paper, let me see, maybe at this point, it's a good time to bring the paper up somewhere, maybe. Where is that paper? Oh, no. Well, let's see. Where did that go? Just a moment. Paper. Oh. Where is my paper? Sorry, I've lost my paper. Okay, just a moment here.
Just a quick question, Frank.
Yes.
It seems like the way that you would implement this is you would apply the clipping to the kernels after each parameter update and before the next forward pass.
He talks about that in the paper, and that's right. But I think it's like, I think he doesn't do it. He mentions like every 100th time. So it's not done like every single like mini batch. I don't believe.
Okay.
It's done like every 100th mini batch. So I mean, there's nothing to prevent you from doing that, but there's some computational costs to that. So I think he kind of limits it.
Okay.
Okay. Oh, let's see. Before I run out of time. Okay. Let me see. Where am I here? Review. Okay. What?
I sent a link to the chat window, Frank, for the paper, for the PDF file. Just click on that and click over it.
Okay, for some, like, let me see here. Okay, let's see.
The chat window of the Zoom on the side. Oh, there you go.
Okay, sorry. Yeah, okay, so let's talk about these. Here's the time it takes. As you can see, if the full matrix method is like totally impractical, right? It's just off the charts past a certain level. And, and these are like small. If you look at these, 3x3 convolution, 16x16 images, 11x11 convolution, 64. These are small, we're using like 224 by 224 by whatever. So then the important thing, I guess, this whole thing is like the performance. How does it work? Well, this clipping threshold, right? Unfortunately, that is like a hyperparameter, right? Like in many training algorithms, you've got this threshold, like you've got some kind of L1, L2 regularization, and it has some kind of lambda or whatever, and you have to hyperparameter optimize that. And this is like no different, unfortunately. You still got to figure out what's the best clipping value to use. And so like no clipping, well, we're here. If you get some clipping, then it improves it. But like, as I mentioned in the paper, 0.1 actually degrades performance. So you have to pick the best one to get the best performance. So in summary, I would say that, 14% is a good improvement. I don't really have a good feel for if that, state of the art for CFAR10. I know there's a lot of other things you can do to data besides regularization to improve performance. But it, computational wise, it seems like it's worth, it's not totally ridiculous the way they've implemented it. So I guess I would say that perhaps in the future this might be built in to some of the some of the frameworks. Maybe it'll be put into TensorFlow or Keras or something like that, and people will start using it. But one thing about this paper is that it is very it's useful, to think about the transformations and the structure of the transformations and how those transformations relate to regularization. So,
Frank?
So, yes.
Hey, yeah, I had a question. So, if it was I mean, I assume that it was like already kind of known that, the convolution could be like expressed as a Fourier transform. So is it actually implemented in like, so meaning is the technique of doing a Fourier transform and doing it in the frequency space, is that actually implemented in like the popular deep learning softwares like, PyTorch or TensorFlow?
I don't believe that it is implemented. I mean, I know that there are certain, I've read papers where they do use those. Of course, it's the efficiency is dependent on the order of the it's n log n. So you have to have a certain level of n before it beats the other method.
Yeah, actually, can I add a couple things? I was actually just looking at those papers. Jan LeCun has a paper, and I saw another paper referenced to that Jan LeCun paper from about like 8 years ago or something, that they used Fourier transforms to calculate the convolutions. The Fourier transform, fast Fourier transform is n log n, where convolution in the original physical domain, space domain, is n squared, but there is an overhead. And you have to exceed a certain number, maybe after 600 or something, the returns start to become positive. The n log n beats the n squared. So there's some overhead. And there's also another drawback. When you're in Fourier domain, all the convolutions, if you visualize the convolution filters, it's not going to make sense. Whereas if you're doing the convolutions in the space domain, the kernels are actually, if you look at the kernels, visualize the kernels, you'll see physical patterns like circles or corners or diagonal edges and whatnot. When you're working in Fourier domain, the interpretability basically goes out the window. That's another drawback. But I think the answer to that is, as Frank has said, n has to be bigger than a certain number for the Fourier transform.
Yeah, I mean, typically, we're talking about 224 by 224. So in our convolutions. So yeah, I mean, and then so perhaps in the future. But for now, I guess, like the things you mentioned, it's not as practical. But of course, in this paper, the fast Fourier transform is used and efficiently. So, you know, how they're using it, I think, is different than the way you would use it in the layers of a convolution. So, for calculating the singular values.
Yeah, as I understand, they are combining it with the domain filtering to regularize the model in a new exotic way. And they claim to reach better generalization to achieve lower test errors. But again, you know, most of these papers, they just run their tests on small data sets. So I don't know how this would perform on real world data sets.
Well, that's a good point. If you look at this diagram, this is the amount of time it takes, right? So it's like 5 times 10 to the 4th seconds. That's a long time, right? I mean, that's 10 hours or something like that. I don't know.
10 to the 4, let me work it out. Let me open my notebook here.
Of course, I don't know what they're training it on, but assuming it's a single GPU, I mean, that's a long time for, you know, CFAR time.
Almost 3 hours, 10 to the 4th seconds.
Okay.
2 hours and 45 minutes.
Yeah, that seems like a lot. I mean, I would think that, you know, if you were to apply that to the entire ImageNet, you know, it would be, but perhaps that's the next step, you know. We'll try it on ImageNet. And then I personally, I don't know what the state of the art on CFAR 10 is, but maybe like 5.3% is not that great. I don't know.
What's the resolution of the CFAR 10 images?
I think they're 96 by 96.
Yeah, that's what I remember. And it's a much smaller data set with only 10 classes.
That's another thing, you know.
I think
the scalability of this to 224 by 224.
Yeah.
So, well, I'll let everybody go soon, and you know, let me know if you have any questions, or like if you're interested in this, like, and you want to add more things to that notebook that would make it better. You know, maybe we can, and you know, or these slides, you know, we can do that as well. Maybe put it somewhere. All right, I'll let everybody go. Thanks a lot.
Thank you, Frank.
Thank you, Frank. That was excellent.
All right, bye.